Hi. With this video, I want to talk about frequency response functions. So this is the other way we can think about studying the dynamic response of a system. So here, instead of an impulse load like we did with the impulse response function, we're going to think about harmonic loading. Okay, so I'm going to have the load on the system be something periodic, like a cosine function or a sine function. And I want to think, how is my system going to respond to that? Okay, and so this is useful, particularly when we think about the loading in the frequency domain. So I can think about taking my f of t loading as a function of time and transforming that to a series of periodic functions as a function of frequency, omega. Right? And I can do that transition using a Fourier transform. And then if I have my loading characterized as a bunch of periodic functions that vary as a function of omega, for each of those omegas, I can then use what we call a frequency response function for my system. Oops. So this is this capital H subscript x of omega. And that's going to tell me, how does my system respond to periodic loading with frequency omega? Okay. And so then the output of that is going to be a response of my structure x as a function of omega. So I'm going to get a periodic response if I load it with this periodic function. And as a function of omega, those amplitudes of those periodic responses will vary. And then I can do an inverse Fourier transform, if I want to get back to loading as a function of time. Or I may just keep my description as a function of frequency. Okay. So that's kind of the idea, and that's why this frequency response function is important. So today, in this video, we're just going to think about the loading that being a periodic function and the response being a periodic function, and saying how do the amplitudes of those two relate to each other. Okay. So we're going to think about harmonic loading. So I'm going to apply that my f of t, which is my p of t over m. I'm going to apply a function sine omega t over m. Right? So it's just a sine function varying in time. I'll divide by m to keep my units simple. And then the omega is the omega that I'm loading my system with. And then the omega naught is the undamped frequency of my system, as we were using before with the impulse response functions. Okay, so there's a loading frequency omega, and then there's a structure frequency omega naught. Okay, so given this framing where I'm using this underlined term as my loading now, and I'm thinking about steady state, so I don't have that kind of initial impulsive response, but when the structure settles down to oscillations that are just a sine function, what I want to know is, what is the response of the structure? And kind of more narrowly, but very helpfully for us in this framing, I want to know kind of how big is the max of x of t relative to the max of f of t. Right. And that ratio is going to depend on the properties of the structure, the omega naught and the zeta damping, and it's going to depend on the frequency of the loading, the omega, as well. Right, so as a function of the loading frequency and the properties of the structure, how big does my response get for a given amplitude of load? Okay, so first let's set up kind of one way to think about solving this, and then we'll move to what's actually maybe a little less intuitive at the beginning, but actually much more effective way of solving this problem. So I could say, right, well, if I'm loading this structure with the sine omega t, then let's say my response is equal to a sine of omega t term plus a cosine of omega t term with some constants, and then I need the 1 over m in there to do some normalization. Well, it doesn't really matter, because whatever I don't put in there gets pushed into the constants, the c1 and the c2. Right? So I could take this x, and I could substitute that in here. Then I could take the derivative of the x and substitute it in for the derivative term, and take the second derivative and substitute it in. And then we could solve for the constants, c1 and c2, right? Because everything would be defined except the c1 and c2. So we could do that. That would be similar to the previous impulse response work that we did in the previous video. And what we would see is that we would get the max of x of t that would equal 1 over m square root c1 squared plus c2 squared. Okay, and we could continue on, but this is actually a little bit more of an awkward framing. There's a more clever way we can do this that we're going to switch to here. So let's just jump to this one because it's more interesting. I'm going to rewrite my loading as p of t equals e to the I omega t, where e to the I omega t is equal to cosine omega t plus I sine of omega t. And this I is this imaginary number that's equal to the square root of -1. Okay? And so that's, on one hand, I remember the first time I saw this, a little bit weird that we're introducing imaginary numbers into our loading. It turns out to be really useful in that it gives us nice clean derivatives, and we can do our math really simply down below. And then we can do some adjustments to have to not deal with the imaginary number in our final solution. So don't worry about it too much. Okay? But the idea here is I've still got a harmonic function for my loading, right? I've still got a cosine term and a sine term. I just introduced this imaginary number here along the way. Don't worry about it a ton for now. Okay? And then the beautiful thing is that the derivatives of this are going to be easier to deal with than the alternate derivatives if we just used like a sine and a cosine with some leading constants on them. Okay? So if we do it this way, then what I'm going to say is, so my loading is e to the I omega t, and let's assume that my response is going to be some constant, which is my frequency response function, capital H sub x of omega. So it's a function of the omega that I load with, multiplied by that loading function. So, or equivalently, the frequency response function times e to the I omega t. Okay? So my response is proportional to my p of t exactly through this frequency response function. And that's going to define the ratio between the loading and the response. Okay? And if I set up x that way, then my derivatives are really easy. So I could say, then the first derivative of this, right, it's the h sub x of omega is not a function of time, it's just this amplitude modulator. So it just looks like a constant, with regard to this derivative. So that just sits there. And then the e to the I omega t, when I take that derivative with respect to t, I'm going to get an I omega down out front, and then the e to the I omega t remains. Okay. And then if I take another derivative to get to my second derivative, right, so the frequency response function, again, looks like a constant. It just stays there. The e to the I omega looks like a constant. It stays there. So again, I just take a derivative of e to the I omega t. That brings down another I omega. So I've got I squared omega squared. The I squared is just equal to -1. So I end up with a minus omega squared e to the I omega t. Okay, so there's my x of t that I've assumed, the functional form, and then the first and second time derivatives. Okay? So I'm going to take those three results and plug them into my differential equation. Right? So where I have an x double dot, I'm going to substitute in this term that I've just solved for with my derivative. Where I have the x dot, I'm going to plug in the x dot term I solved for. And where I have the x, I'm going to plug in this, just the frequency response function times I omega t. Okay? And what I see is that every term on the left-hand side has the frequency response function, and every term has the e to the I omega t. So let's just start by pulling those out front here. So I have the frequency response function, h sub x of omega, e to the I omega t. And then now let's put the rest of the stuff inside square brackets. So for the x double dot term, all I have left is the minus omega squared. For the x dot term, I have the leading coefficients from the x dot already. So the 2 zeta omega naught. And then from the x dot term up here, I've got an extra I omega that I need to keep. Okay, and then for the x term, I just have an omega naught squared. and the x, all the stuff associated with x is already sitting outside the square brackets. Okay? And then on the right-hand side, I have e to the I omega t divided by m. Okay, so I see on the left-hand side and the right-hand side, I have the e to the I omega t, so those are gone. So that's the beauty of posing my loading as e to the I omega t, is it just cancels out immediately, and I'm going to simplify my math a lot here. Okay, I still do have this one imaginary number floating around in here, but that's not too bad. Okay, so next slide, let's regroup this thing a little bit. So what I see is that I've got the frequency response function times the square bracket here, and on the right-hand side, I just have a 1 over m. So since I want to solve for this frequency response function, I'm just going to divide both sides by this square bracket, and let's rewrite that on the next slide. Maybe I can leave it on the screen here. So I see that the frequency response function h sub x of omega is equal to, we got kind of a 1 in the numerator, and then we have m from the right-hand side, and then the stuff in the square brackets, minus omega squared plus 2 zeta. Let's rearrange. Let's pull the I out in front since it's not a variable. So 2i zeta omega naught omega. And then we have a plus omega naught squared. And we could rearrange this a little further. So let's do a little bit more here on the next line. So I'm going to take this as kind of 1 divided by m. And then let's take omega naught squared minus omega squared up front. And then I'll take 2, yeah, that's fine, 2i omega naught omega on the right. Okay, and the reason I did that, I just wanted to group all of the real numbers, the omega naught and the omega squareds, together, and then I've got this term over on the right, which has got the imaginary number, the I, in it. Clean up a couple of these letters for you. Okay, and the functional form here, so this looks something like 1 over m times c plus I d, where c and d are just some collections of constants. Right, so I've got kind of c is all that stuff, and then d would be the 2 omega naught omega, kind of everything but the I here. Okay, and the reason I'm going to write it that way is because I'm going to get a complex conjugate in just a second. So what I'm going to look for is the modulus of this frequency response function. So I'm going to write a vertical bar h of omega, h sub x of omega. So where the bars indicate what we call a modulus, and it's going to measure like a distance for us in just a second, and it's going to equal the square root of the frequency response function times its complex conjugate. So I'm going to indicate that with an asterisk. Where h sub x asterisk of omega equals a complex conjugate. And specifically what we do with the complex conjugate is all the terms that were imaginary, all the i's, we make them a negative I. So it's going to equal 1 over m times c plus c minus I times d. Right? So the c part gets unchanged, just the part with the imaginary number gets to become negative. All right? So when we look at this equation here, right, I've got a square root, then we've got 1, we've got an m squared, because both the frequency response function and its complex conjugate have an m out front. And then we get C plus ID from the h of omega term, and then a C minus ID from the complex conjugate term. The whole thing's in the square root. Okay, and then we can simplify this a little bit. So the C times the C gives us a C squared. Then the inner term gives us a ICD. The outer term gives us a minus ICD, which cancels. And then the last two terms, we get an ID times a minus ID. So we get minus I squared D, but the I squared is a minus 1 as well. So we end up with 1 over m squared C squared plus D squared, where that complex conjugate calculation canceled out the imaginary number. So we started off with that imaginary number, which set up our math nicely. And then we take this complex conjugate to get rid of our imaginary number. Okay, so now the C's and the D's we've got defined up top in red. So let's rewrite this one more time, substituting back in what C and D were. So we've got a 1, and then in the denominator we've got m squared. And actually, we can pull the m squared outside of the square root, so let's just keep that outside. The 1 can come outside as well. I'll just put the square root down here. So the C, we've got omega naught squared minus omega squared. And the D, we've got 2 omega naught omega squared. So that stuff is all in the square root still. And then it's all in the denominator of our fraction as well. Okay, so we made it. And that modulus that we just solved for here is equal to the max of x of t divided by the max of p of t. Okay? So it gives us the amplitude of the biggest value of this ratio. All right? So the imaginary numbers and things had some phasing and stuff in there. But this modulus, when we take the complex conjugate, it tells us, for the peak of the p of t harmonic, how big is the peak of the x of t harmonic, and what's the ratio between those two. And that's the thing we're interested in, trying to look at the response of our system. Okay, so next slide, I've got that frequency response function that we derived just written out. So this upper right equation is exactly the thing from the previous slide, the last line. And I've got it plotted here. So we've got the modulus of the frequency response function on the y-axis, and then we've got omega, the frequency of the excitation, on the x-axis. Okay, so let's, and I've got this plotted for 3 different values of zeta. So we go from omega close to 0 on the left to big omegas on the right, and let's talk through kind of some of the patterns here in this figure. So let's see. So the one thing to note is that the peaks are, let's go down a little further here. Okay, so the peaks of these functions occur where we're getting resonance, and it's where the omega that we're exciting it with, the system with, is about equal to omega naught, the natural frequency of the system. Okay. And so if the excitation omega is very similar to the omega naught, or the omega d, which is quite similar numerically for lightly damped structure, then we get these big responses, right? So if I've got a system that wants to vibrate at frequency omega naught, and I put in a harmonic vibration close to omega naught, I'm going to get a really big response out of the system, right? And if it's undamped, so zeta equals 0, then things will explode to infinity, right? This term here where omega naught minus omega, if those two are equal to each other, this is 0. And if zeta is 0 as well, then the whole denominator goes to 0, and this function will go to infinity. All right? As long as zeta is not equal to 0, then I've got a little bit of a non-zero term here on the right. So even if this term goes to 0, when omega is about equal to omega naught, then, so as long as zeta is non-zero, it won't be infinite, but as zeta gets small, this term will be small and the peak will get bigger. Right? So maybe we can make a general note here that we can say h sub x of omega gets smaller as zeta gets bigger. Okay, so bigger zeta here is going to make this term bigger, and the frequency response function will get bigger, right? So these functions just, for all frequencies, they get smaller as the zeta gets bigger. It's obviously the impact is much smaller on the right and the left. That's we'll talk about that in just a second. But you can see that the responses get smaller. So more damping in the system means that we're going to get a smaller response. So that would make sense. Okay, so then let's look at the limits on the sides. So as we go kind of heading this way towards big omega, this is the case where omega is a lot bigger than the omega naught, where the peaks are occurring at. So what we can see is that if omega is big here, if that omega gets big, let me do it with this highlighter. So that omega gets really big compared to omega naught, and this omega gets really big compared to omega naught. The omega squared term is going to kind of dominate, right? If this is a big number. So what we're going to end up with is the omega naught term is not going to matter much because it's a lot smaller. The second term over here is not going to matter a lot because it doesn't have a square on the omega. So what happens is that this frequency response function we can simplify down dropping those other terms, and it's about equal to 1 over m omega squared. Right? So I've got an omega squared inside of a square root. So I'll just drop the square root, and we've got something that looks like this. So what's happening is that we're mass controlled. And say, right, that our response is a function of the excitation, omega squared. And so as that gets bigger, the response will get smaller. And then the mass of the structure, right? So here we just have this inertial response. The excitations are very fast relative to the frequency at which the structure wants to resonate, the smaller omega naught. And so it's just gonna kind of sway back and forth. And the lighter the mass is, the bigger the response. And the bigger the mass is, the smaller the response. Okay. Then over on the other side at the far left, right, so we have, over here, we have omega that's heading towards 0. So this is a very small, or very slow excitation, right? The frequency is tending towards 0. And we see all these lines converging over here. So what's going on here? So in this side, the modulus what's it want to do? So if I look at omega close to 0 in my top equation, so I'm going to have like a minus 0 squared here, so that's not going to play a role. And then the omega heading towards 0 here is also going to zero out this whole term. So all I'm going to be left with is the omega naught squared over here. So it's omega naught squared inside the square root. So we end up with 1 over m omega naught squared. So in this case, these are just properties of the structure, not properties of the excitation, right? The omega has disappeared. And remember that the stiffness of the structure, K, is equal to the square root. K is equal to, omega naught is equal to the square root of K over M. So omega naught squared times M is equal to K, which is the denominator. So what this is equal to is 1 over K. All right, so this is what we'll call a static response. So over here, the excitation is very slow compared to the frequency at which the structure wants to oscillate. So the structure sees this as a static force, basically. And so the amplitude of this very slowly varying response is going to influence the response of the structure relative to the stiffness of that spring. And so the stiffer the spring is, the bigger the K, the smaller the response. Right? So all we're dealing with on the left-hand side is the static stiffness of the system. All we're dealing with on the right-hand side is the mass of the system. And notice the damping doesn't influence either one of those. The damping term kind of disappears when either omega or omega naught gets, when omega gets big or small. So in the middle, the damping is very important. We can see this big difference between those three lines. On the right and the left, the damping doesn't matter very much. It's just the stiffness and the mass on the left and the right, respectively, that govern this response. Okay, so that's kind of the concept of how the system's responding to harmonic excitation. And here's our formula, and we've talked through how we might derive that frequency response function. We could derive a similar frequency response function for a different differential equation if we wanted to. Okay, so big picture, heading towards stochastic process analysis, we're going to take that f of t and put it, make it stochastic, but then we're going to switch and describe it in terms of its frequency content rather than its variation as a function of time. So if we describe the excitations in terms of frequencies, this frequency response function is really useful to say, well, how would the system respond to excitations at those frequencies? And so then we'll be able to look at frequency content of the system's response to a more complex excitation consisting of multiple harmonic loads superimposed. We'll have the tools when that time comes. Okay, so some learning objectives from kind of these series of videos. First is just to have a high-level understanding of what's the type of dynamics problem we're looking at. Right, so we're going to look at some sort of a physical system, generally that's got a mass and some stiffness and damping, generally speaking. And we can write that behavior of that system down as a differential equation. And if we can do that, then we can solve the problem in a couple ways. So, so far we're thinking primarily about this Duhamel integral approach. So the idea is, with this one, is that we can define the force as a series of Dirac delta functions. Multiplied by constants to vary the amplitudes. And then in that case, the response is going to be a superposition of impulse response functions. Okay. And so we went through in our videos how to derive one of those impulse response functions. Okay. Then the second approach that was the focus of this particular video was the frequency response functions. So there we're going to think about the force as a harmonic function. We didn't yet get to the point where we superimpose multiple harmonic functions. That'll be coming later. But we'll have a kind of an analogous process where we superimpose a bunch of harmonic functions, and then we say, well, the frequency response functions can be then superimposed to understand how the system might respond to that superposition of periodic functions. Okay, so there's some basics of dynamics, hopefully useful review for those of you who've seen it before, or maybe an introduction for some folks. And that should give you a foundation for looking at random vibrations problems down the road. Okay, thanks.